So this is going to be my last video on the Laplace transform. I've realized that there are actually a lot of good resources online to learn more about Laplace transform. In particular, I'd like to recommend Khan Academy's great playlist on the Laplace transform. They have a lot of examples and how it applies to differential equations, and they even have, I think, a few examples where you solve a linear differential equation using the Laplace transform. So I'll link to that in the description. So today what we're going to do for this last video is calculate the Laplace transform of e to the at. Now you shouldn't confuse that with the e to the negative st that's sitting over here. Um, this e to the at is a completely separate function. So in this context, my e to the at is the function that I'm going to be Laplace transforming. So just writing it out, with the definition of the Laplace transform, I get e to the negative st e to the at dt. And this is going to be equal to, by using the laws of exponents, this is going to be equal to e to the power t times a minus s, and then add a dt just to close the integral over there. And this is going to be equal to, what I'm going to do right now is just flip the signs in the exponent over here. So I'm going to write e to the negative t, and if I add a negative over there, I need to add one inside, so s minus a dt. But I know what this is. It is just the antiderivative of this thing evaluated at infinity and 0, and that the antiderivative of our function over there is just going to be e to the negative t times s minus a, and then you put a negative sign in front, divided by s minus a. I evaluate that at infinity, I evaluate that at 0. Okay, cool. So now what we're gonna do is, well, evaluated at infinity. What is e to the negative infinity? E to the negative infinity is 0, so all this stuff isn't going to matter. It's just going to be a big fat 0. And from that I'm going to subtract off something, and that something is going to be, well, what's e to the negative 0? Negative 0 is just 0. All this goes to 0. So what I get is negative, e to the 0 is 1, by the way. So I get negative 1 over s minus a. Rewriting that and cancelling out the negative signs, what I get is 1 over s minus a, and that is our answer for the Laplace transform of e to the at. Again, pretty straightforward. This wasn't a really complicated Laplace transform, but there's an interesting fact to note over here. So the first thing you probably might have noticed is, what happens if we plug in a equals 0? So now let's just take the case where a equals 0. Then I know that the Laplace transform of, well, e to the 0. Oh, but for now let's just keep it as e to the power at, where a is 0. I know that the Laplace transform is going to be 1 over s minus a. And what is this equal when a is equal to 0? It's just equal to 1 over s. But 1 over s looks familiar, because 1 over s is the Laplace transform. Sorry, I got the symbol a little messed up there, but it's the Laplace transform of 1, which makes sense because e to the 0 is 1. And it just a quick confirmation that what we've been doing over the last two videos actually it does make sense. But even more broadly speaking, it tells you that what the exponential function does in terms of Laplace transforms is it shifts the Laplace transform in the s domain. So let me just quickly explain what that means. So let's say I have some function f of t, right? And if I let's say I plot the graph of f of t, and I don't know, it maybe looks something like that, right? And if I want to shift this function by a few units, let's say a units to the right, what I would do is I'd plot f of t minus a. What this would do is shift it a units to the right, so I'd get something like that, where this distance over here is a, right? That's how you shift functions. But what if I give you a function and I say, okay, I don't care what you do to the function, but I want you to shift the function's Laplace transform. Oh, sorry, I guess that arrow shouldn't be there. To give you a better picture, let's say I have, again, some function f of t, but this time I don't want to shift f of t to f of t minus a. That's not what I want to do. What I want to do is shift the Laplace transform of f of t to a function where the Laplace transform itself is shifted. So if I plot the function over here, I don't know, let's say that this function is the Laplace transform of f of t. How do I shift this Laplace transform of the function? By just playing around with the function. And it turns out the answer is multiplying the function by e to the at. So if I want to shift the Laplace transform, so I'll just write that down. To shift the Laplace transform of f of t, what you do is multiply by e to the at. And to be specific, this is a units to the right. And that's exactly how, well, it's not exactly how, but it's somehow similar to what you might do for regular functions. When you want to shift regular functions up here, what we did is, if you want to shift it a units to the right, you get this t minus a. But over here, if you want to shift the Laplace transform of f of t a units to the right, you'd multiply it by e to the at. And that's an interesting property of the exponential function in terms of its Laplace transform. Its job or its duty is to shift the Laplace transform of the function left or right.